Alright. Here I got some cool stuff I am about to share. Linear algebra explained in just 4 pages. 1, 2, 3, and 4. So let's see. So linear algebra, vector B. Linear algebra is the math of vectors and matrices. Let n be a positive integer, let an r denote the set of real numbers. Then r to the power n is the set of all n tuples of all real numbers. A vector b, which is a member of r to the power n, is an n tuple of real numbers. The notation epsilon s is read element of s. For example, consider a vector that has 3 components. V bar equals to v1, v2, v3. So it is an element of set R cube. A matrix A, which is an element of R to the power m times n, is a rectangular array of real numbers with m rows and n columns. For example, a 3x2 matrix looks like this. A equals to a 1 1 1 2 2 1 2 2 3 1 3 2. All of them are member of R. So A, the matrix A itself, is a member of R power 3 times 2. So the purpose of this document is to introduce you to the mathematical operations that we can perform on vectors and matrices, and to give you a feel of the power of linear algebra. Many problems in science, business, and technology can be described in terms of vectors and matrices, so it is important that you understand how it works. So prerequisite: understanding of high school math concepts, variables, equations, fundamental arithmetics, etc. etc. You should also be familiar with functions that take real numbers as input and give real numbers as outputs. So a function, a mapping from real number to real number. Recall that by definition the inverse function f inverse undoes the effect of f. If you are given a function of x and you want to find x, you can use the inverse function as follows: f inverse of f of x equals to x. For example, the function fx is equal to ln of x has the inverse f inverse x equals to e to the power x. Similarly, inverse of g of x equals to root of x is g inverse x equals to x squared. Yeah, it's very reasonable. Inverse of root of x is x squared. Vector operations. We now define the math operations for vectors. The operations we can perform on vectors: u dash equals to u1, u2, u3, and v dash equals to v1, v2, v3 are addition, subtraction, scaling, norm, dot product, and cross product. So u plus v is understandable. Alpha u bar multiplying with a scalar, u dot v u1 v1, u2 v2, u3 v3, norm u bar u root over u1 square plus u2 square plus u3 square. U cross b, that is the vector product. That is a bit of different thing, a bit of tricky thing. It is not very used anywhere, is it? Anyway, u cross b equals to u2 v3 minus u3 v2, u3 v1 minus u1 v3, u1 v2 minus u2 v1. The dot product and cross product of two vectors can also be described in terms of the angle theta between the two vectors. The formula for the dot product of the vectors is u dot v equals to magnitude of u times magnitude of v times cos of theta. We say two vectors u dash and v dash are orthogonal if the angle between them is 90 degree. The dot product of orthogonal vectors is 0, so u dot v equals to magnitude of u times magnitude of b times cos 90 degree, and cos 90 degree is 0. So there you go, the orthogonal vector dot product of orthogonal vectors comes to 0. The norm of the cross product is given by u cross b, magnitude of u cross b equals to magnitude of u times magnitude of b times sine theta. The cross product is not commutative, so u cross b is not equals to b cross u. In fact, u cross b equals to minus b cross u. Let's move on to matrix operations. So addition plus c equals to a plus b, of course assuming they have the same dimensions, same rows and same number of columns, same number of rows, same number of columns. So Cij equals to Aij plus Bij. Subtraction same. Important is the multiplication, the product, matrix product. The product of matrices A, which is a member of R power m times n, and B, which is a member of R power n times L, is another matrix C, which is a member of R power m times L. So number of rows is as in the number of rows in A, and number of columns of C is equals to number of columns in B. Number of rows equals to number of rows in A, number of columns of C equals to number of columns in B. We will soon see why. So we have this M11, A21. Notice that the A and B has equal as number of columns in A equals to number of rows in B. Number of columns is, so we have two A11, A12, and B11, B12. So this row times this columns values make up the first number in the product matrix C. A11, B11 plus A12 times B21. For example, if you want to find C22, that will be A21, B12 plus A22, B22. Matrix inverse denoted as A inverse, and matrix transpose denoted by transpose superscript T. So transpose of a matrix is where the rows becomes columns, columns become rows. So alpha 1, alpha 2, alpha 3, this row becomes alpha 1, alpha 2, alpha 3, first column. Second row becomes second column, beta 1, beta 2, beta 3 becomes second column, beta 1, beta 2, beta 3. Matrix stress of a matrix is equals to summation I equals to 1 to n aii, so it is going diagonally. Determinant denoted by det A or A. Note that the matrix product is not commutative operation, so AB is not equals to BA, of course. So next, moving on to matrix vector product. Y bar equals to AX bar. So matrix product, here we have matrix vector product. It is a special case, and so there is one it can be seen as a matrix product with where one matrix is just have one dimension, one either number of rows or number of columns is 1. For example, here y dash equals to ax dash. Y is 3 by 1 vector, and a is a 2 by 1 column vector, and x1, x2, x is 3 by 2 matrix A, and 2 by 1 column vector x results in the 3 by 1 vector y. So a matrix multiplied by a vector turns out to be another vector. Let's move on to linear transformation. The matrix product vector product is used to define the notion of a linear transformation, which is one of the key notions of the study of linear algebra. So manipulation by a matrix A, which is member of R power m times n, can be thought of as computing a linear transformation TA that takes n vectors as input and produces m vectors as outputs. So TA is a mapping from R to the power n to R to the power m, where we are multiplying by matrix A with m number of rows and number of columns. So multiplying by a matrix is going to become thought of as a linear transformation. Alright. So a linear transformation, what is it doing? It is turning an n by 1 matrix, n by 1 vector into an m by 1 vector. For example, in the example above, we had this x which turned from a 2 by 1 vector into a 3 by 1 vector. So you can stack up transformations. So apply one transformation on top of another. The combined effect of applying the transformation TA followed by TB on the input vector X is equivalent to the matrix product BAX. So now let's take a look at vector space. A vector space consists of a set of vectors and all linear combinations of these vectors. So the vector space S equals to span of v1 v2 consists of all vectors of the form P, so alpha v1 plus beta v2, where alpha and beta are real numbers. We now define three fundamental vector spaces associated with the matrix A. Alright, let's see. The column space of a matrix A is the set of vectors that can be produced as linear combinations of the columns of the matrix A. So this is the column space coming out of the columns of the matrix A. C of A to Y in a set of Y member of R power m. Remember that A has dimensions m by n, so m rows and columns. C of A, the column space is consisting of vectors in R power m, where y equals to ax for some x in R power m. Fair enough. The column space is the range of the linear transformation TA, the set of possible outputs. You can convince yourself of this fact, of course. So this is the range of the linear transformation TA. For instance, the vector ax dash here, where x is the column vector, so it contains x1 times the first column of A. X is the column vector x1, x2. There you have it. So first column of A, and x2 is multiplied with second column of A. So x1 multiplied with one column vector, x2 multiplied with another column vector. So varying over all possible inputs x dash, we obtain all possible linear combinations of the column of A, hence the name column space. So x1 and x2, so x1 times column first column plus x2 times second column, it is giving, so the column space is the range of the linear transformation TA. The null space Na of a matrix A, which is a member of R power m times n, consists of all the vectors that the matrix A sends to the zero vector. So null space of A equals to x member of R power n given x equals to 0. The vectors in the null space are orthogonal to all the rows of the matrix, of course. You can see this from the row picture R. The output vector is 0 if and only if the input vector x is orthogonal to all the rows of A. So the row space of a matrix A denoted by Ra is a set of linear combination of the rows of A. The row space Ra is the orthogonal complement of the null space Na. This means that for all vectors V in Ra and all vectors U in R, W in null space, we have V times W equals to 0. Together the null space and the row space form the domain of the transformation TA. R to the power n equals to null space of A orthogonal direct sum of Ra. Ra null A. Alright. Maybe a few more examples will make it clearer. So we have here column space, set of vectors that can be produced as linear combinations of the columns of the matrix A. Then we have the same row space, set of linear combination of the rows of A. And we have null space, consists of all the vectors that the matrix A sends to the zero vector. So it becomes 0 on all those vectors. If A multiplies, A is applied to that vector, it turns out to be 0. Then we have inverse of a matrix such that A inverse times A equals to the identity matrix I, where all the values along the diagonal is 1, otherwise 0. So T1x equals to 1x, Ix is x. Identity transformation. Okay. The matrix inverse is useful for solving matrix equations. Whenever we want to get rid of the matrix A in some matrix equation, we can hit A with its inverse A inverse to make it disappear. Yep. For example, to solve for the matrix X in the equation X A equals to B, multiply both sides of the equation by A inverse. From the right, X equals to B A inverse. To solve for X in ABC XD equals to E, multiply both sides by D inverse, then by A inverse on the right, then B inverse and C inverse in that order from the left. So D inverse on the right, and by eventually we'll find X equals to C inverse, B inverse, A inverse, E, D inverse. So let's see some conclusions. Of course, solving system of linear equations. 1x1 plus 2x2 equals to 5, 3x1 plus 9x2 equals to 21. So here we can see we can start an augmented matrix 1, 2, 3, 9, the coefficients, and 5 and 21, the value on the right hand side. So Gauss-Jordan elimination procedure. The first step is to use the pivot in the first column to eliminate the variable x1 in the second row. So we have 1 and we have 3, so subtract row 1 3 times from row 2, which turns into, so it turns the first column of the second row becomes 0. Next we create a pivot in the second row using R2 is to 1/3 R2, so divided by 3. So the augmented value is also divided by 3, 6 becomes 2. We now start the backward phase. We are doing the Gauss-Jordan elimination procedure. We now start the backward phase and eliminate the second variable from the first row. So we have 1, 2 and augmented value 5. So to eliminate the second variable 2, we subtract the second row from the first row twice, 2 times. So which means second variable becomes 0 and the augmented, like the value on the right hand side, 5 minus 2 times 2, 4, so 5 minus 4, so it becomes 1. So we have now the identity matrix. The matrix is now in reduced row echelon form, which is its simplest form. It could be in the solutions are x1 is 1, x2 is 2. So next we have another method using inverse, then using row operations. Inverse, creating inverse using Gauss-Jordan elimination, using elementary matrices, using a computer to find the inverse. Then we have the basis as another topic. Intuitively, a basis is any set of vectors that can be used as a coordinate system for a vector space. So unit vectors x-axis and y-axis, the vector b can be described as a coordinate pair bx by. So where v equals to bxi times I plus by times j I hat and j hat, where I equals to 1 0 and j equals to 0 1 are unit vectors, and also they are the basis. However, other coordinate systems are possible. A basis for n-dimensional vector space S is any set of n linearly independent vectors that are part of S. Converting a coordinate vector from the basis B to the basis Bs is performed as a multiplication by a change of basis matrix. Change of basis matrix. So change of basis matrix, what it does, it change from basis B to basis Bs. Alright. So it is actually an identity transformation. The vector B remains unchanged. We are simply expressed with respect to a new coordinate system. And the change back, so the change back from BS basis to the BE basis is accomplished using the inverse matrix. Matrix representations of linear transformations. We have already seen that r to the power n to r to the power n, or r squared to r squared. As the first example, consider the transformation pi x, which projects vectors onto the x-axis. For any vector b equals to bx0, you have pi of x. Pi x b dash equals to bx0. The matrix representation of pi x is, alright. Then we have this cos theta minus sin theta cos theta. This is a rotation vector rotating by an angle theta. The dimension of a vector space is defined as the number of vectors in a basis for that vector space. So here span 1 0 0 0 1 0 1 1 0, so we have the dimension 3. Seeing that, we might think that the S is 3-dimensional. This is not the case, however, since the three vectors are not linearly independent, because 1 0 0 and 0 1 0 can form 1 1 0. So actually 1 0 0 and 0 1 0 are the two sufficient ones. So the dimension is 2. There is general procedure for finding a basis for a vector space. So you can use the Gauss-Jordan elimination procedure to accomplish this task, of course. The non-zero rows in the RREF of the matrix. What is RREF? Let's go back. The RREF, reduced row echelon form. Echelon form, reduced row echelon form. Now let's look at using elementary matrices. Have you seen that? Yeah, we have. Row space, column space, and rank of matrix. So row space is we already saw that before. Column space, we already saw that. So we have a reduced echelon form which contains 3 pivots. So the vectors 1 3 0 0, so the 3 row vectors form a basis for row space of A. 1 3 0 0 0 0 1 0 and 0 0 1 0 1. So to find the basis for the column space, we need to find which of the columns of A are linearly independent. So we can see 1 through 3 first column and 3 6 9 second column, basically a multiple of the first column. So 3 6 9 we can ignore second column. Then we have 3 7 9 and 3 6 10, which are independent, cannot linearly independent. So the vectors 1 2 3 transpose, 3 7 9 transpose, and 3 6 10 transpose. So basically first column, third column, and fourth column form a basis for CA, column space of A. Now let's find a basis for the null space. So the null space, remember that the null space is the vectors in R power 4 such that A times X dash equals to 0. Why it should be in R power 4? Because look at A. A is a 3 by 4 matrix. Since it is 3 by 4, so Ax dash, if you want to perform this Ax dash multiplication operation, x dash must be 4 times 1. So x dash must be a member of R power 4. The second column does not contain a pivot, therefore it corresponds to a free variable, which we will denote as. Second column, oh yeah. We are looking for a vector with 3 unknowns and 1 free variable, x1 as x34, that obeys the condition. So here we have reduced row echelon form of A times the vector x1 as x34, which should result in a 3 by 1 0 vector. So we got 1 x1 plus 3, yes, equals to 0, x3 equals to 0, x4 equals to 0, which gives us x1 equals to minus 3s. So we have any vector of the form minus 3s as 0, 0 for any s in R is in the null space of A. So we write null space as A as a span of minus 3, 1, 0, 0. Transpose. So dimension of column of A equals to dimension of row space of A. This is dimension of column space and dimension of row space. Let's take a look. Yeah, because we have 3 rows which are independent and 4 columns, of them 3 of them are independent, so the dimensions are equal, same. This is known as the rank of the matrix. Also, dimension of RA 3 plus dimension of NA, which is 1. Why dimension of NA is just 1? Because it is just a 1 vector minus 3, 1, 0, 0. Transpose. That's what is its span, the null space. Totaling 3 plus 1, totaling to 4, which is the dimension of the input space of the linear transformation TA. Okay, so a theorem is coming up, invertible matrix theorem. There is an important distinction between matrices that are invertible and those that are not, as formalized by the following theorem. For an n by n, so square matrix A, the following statements are equivalent. A is invertible. The reduced row echelon form of A is the n by n identity matrix, of course. The rank of the matrix is n, of course. The row space of A is R power n, of course. The column space of A is R power n, of course. And does not have a null space. Only the 0 vector NA equals to null vector. The determinant of A is non-zero determinant. So, for a given matrix A, the above statements are either all true or all false. All 7 statements are equivalent. The following statements are equivalent. So if A is invertible, then it is the REF of A is an n by n identity matrix. The row space of A is R power n. The column space of A is R power n. All of these are equivalent statements. A corresponds to a linear transformation T A which maps the n-dimensional input vector space R power n to the n-dimensional output vector space R power n such that there exists an inverse transformation T A inverse that can faithfully undo the effects of T A. On the other hand, an n by n matrix B that is not invertible maps the input vector space R power n to a subspace CB which is a proper subset of R power n and has a non-empty null space. Once TB sends a vector W to the 0 vector, there is no TB inverse that can undo this operation. Okay, now let's take a look at the definition of determinants. So it is basically a value and all the other values which are not in that column or that row. So for example, A1, the 2 by 2, it is easy. A11 times A22 minus A12 times A21. For 3 by 3, so A11, which is going to be multiplied by something. What is that something? That is the submatrix which does not contain anything from the row of A11 or from the column, from the same column of A11. So it will be excluding A12, A13 or A21, H1. So there we have it. It is A11 multiplied by that submatrix A22, A23, A32, A33 minus A12 multiplied by A21, A23, A31, A33. These are not in the same column or same row as A12 plus A13 multiplied by A21, A23, A21, A22, A31, A32. If determinant of A is equal to 0, then A is not invertible. Alright, and if determinant of A is not 0, then A is invertible. Now on the final topic of this 4-page thing, eigenvalues and eigenvectors. The set of eigenvectors of a matrix is a special set of input vectors for which the action of the matrix is described as a simple scaling. When a matrix is multiplied by one of its eigenvectors, the output is the same eigenvector multiplied by a constant A. So A times E bar lambda equals to A E dash lambda. The constant lambda is called an eigenvalue of A. So basically multiplying E lambda by a matrix A, that is the linear transformation, is the same as pre-multiplying by lambda, a constant. So lambda is doing the work of A. The constant lambda is called an eigenvalue of A, and E dash is called the corresponding eigenvector. So it is a simple scaling. Action of the matrix is described as a simple scaling. So the set of eigenvectors of a matrix is this special set of input vectors for which the action of the matrix, the linear transformation, is described as a simple scaling. The scaling factor is lambda. Lambda is from the eigenvector, the eigenvalue for the corresponding eigenvector. To find the eigenvalues of a matrix, we start from the eigenvalue equation AE lambda equals to lambda epsilon lambda E lambda. Insert the identity I and rewrite it as a null space problem. So AE dash minus equals to lambda identity matrix times identity matrix time E dash, implying A minus lambda I E dash equals to null. So this equation will have a solution whenever A minus lambda I equals to 0, because the determinant otherwise. Okay, the eigenvalues of A in R power r times n denoted lambda 1, lambda 2 up to lambda n are the roots of the characteristics polynomial P lambda equals to A minus lambda I. The eigenvectors associated with eigenvalue lambda are the vectors in the null space of the matrix A minus lambda I. Certain matrices can be written entirely in terms of their eigenvectors and their eigenvalues. Consider the matrix A that has the eigenvalues of the matrix A on the diagonal and the matrix Q constructed from the eigenvectors of A as columns. So we have a new matrix where only diagonal values are non-zero and they are lambda 1 up to lambda n, and Q equals to the eigenvectors which are the columns for Q. Then we multiply Q, so E lambda 1 times lambda 1 times E lambda 1 inverse coming as a value of A. So matrices that can be written this way are called diagonalizable. Alright, the decomposition of matrix into its eigenvalues and eigenvectors gives valuable insights into the properties of the matrix. Because original page and for ranking or pages by importance can be formalized as an eigenvector calculation of the matrix of web hyperplane. So there we have it, the 4-page linear algebra explained in 4 pages.